Assassins, to another episode of the Dark Assassins podcast, the show that dives deep into not just technology, but the concepts, software, and procedures behind it all, and explains it so simply that even your grandma can understand it. As always, I'm your host, the Dark Assassin. So we got some juicy news this week in the developer community. It's some pretty spicy stuff, so hope you got your milk ready because you might need it for this one. So, allegedly, GitLab is going to start deleting quote-unquote dormant repos from those in the free tier as a cost-saving measure. So, this was first reported by the Register, and as far as I can tell, they're the only one that has any kind of reporting on this. I've seen other articles talking about this same subject, but they always refer back to this main article, the Register. I haven't seen any kind of comment from GitLab on this. And if you're not unfamiliar with what GitLab is, it's a code repo host, essentially. So if you're familiar with what GitHub is, it's basically the same thing. It has a little bit of a different tool set, but it's a way for you to push your local Git repos or your source control on your local machine for your projects up into like the cloud, so your data can be safe, which is kind of the irony. The point of a repo, in the cloud, like on GitLab or GitHub or Bitbucket or any of those other, Git repos, is to be able to have your code be safe. So in the event, your hard drive crashes or your computer bricks or you spill water or coffee or tea or Mountain Dew or, whatever you're drinking all over your computer and it dies, your code is still safe and not, lost forever. And the other great thing about it too is it's a great way, if you're a developer, to basically have a portfolio of all your projects. So when you're applying for a job or something, you can, link that on your resume or something, and then the people that are interviewing you can go look at your Git repos and see what kind of projects you've been working on and that kind of thing. Although for some developers, it's probably best that they don't put their Git repos on their resumes, but that's something that a lot of people do, just kind of as a thing to show, like, this is what I've done, this is what I'm capable of. And then another thing that it's also really good for, and I've personally used it quite frequently, is like referencing back to code projects that you've written. So like I'll, for example, we'll get into later in this episode talking about multithreading and multiprocessing and kind of what that means. And on my I have a Git repo where I, have examples of doing that, one in Python and one in C++, or I guess C rather, but it's C, so it works in C++ too. But one of the reasons I have those up there was to demonstrate the ability, to do multi-threading and multiprocessing, and I've frequently referenced that code on the Git repo. If I don't have, because obviously I won't have it locally on, certain machines, like work computers, for example. So if I need to do something, multi-threading or multi-processing, I need to reference it somehow. So it's, up on my Git repo, so I can just, search my name on there and reference it, and it's great for that. But anyway, going back to this article, so what they define as dormant is basically a repo that hasn't had any issues, commits, comments, or anything like that in the past 12 months. But this only applies to the free tier. So if you pay for GitLab Premium or Enterprise, or I think it might be called Ultimate, but if you're a paying customer for GitLab, this doesn't affect you at all. It's only for us people that are cheap and got the free tier. But so allegedly, according to the registrar, these dormant repos account for 25% of the storage on GitLab, and deleting them would save GitLab $1 million a year in storage costs. Which, sounds, quite a bit. Like, $1 million is, a good chunk of change, like at least for, you and me. For a corporation, I mean, it probably not. I mean, because one thing to keep in mind, according to GitLab's own financial reports, they made $290 million in revenue in the past 12 months. And I believe that's up like somewhere in the neighborhood of, 20-30% from like last year. So they're obviously, as far as making money is concerned, they're not having issues making money. So in the grand scheme of things, $1 million out of $290 million is really not much at all. Like, you're not going to notice that. Plus, the numbers vary, but GitLab is also a multi-billion-dollar company. Multi-billion with a B. So $1 million a year really ain't hurting them. So either there's some like real mismanagement or something going on there, or they're just being cheap, or I don't really know what the deal is. But as far as, from the outsider's perspective, based on the numbers that we have on their finances, it doesn't seem like they should be in this mode of we need to penny pinch in order to, continue operating. Because, I mean, $1 million, if that, like, it seems like it's one of those things where, like, a company, like, this is kind of one of those moves where a company makes it to try to stay alive and, like, delay the inevitable that they're going down. It's kind of seeming like one of those types of things with how, like, desperate this move is. Kind of like when Netflix was like, oh yeah, we're going to crack down on people's subscriptions and sharing passwords, and we're going to jack up our rates and, all this stuff. It's like, I hope that, no one's going to like this decision. And there's been a good amount of backlash from this decision, as you can expect from developers. Which one of the best quotes I think that I saw that sums it up perfectly, at least for me, is, I've been looking for a reason to deploy an on-premise GitLab for educational purposes. I found that reason. And I have to say that I am in that exact same boat, because as you know, fellow listeners of the podcast, I love talking about home labs and all the stuff that I host at my house, in my data center, as people like to call it. And one of the things that I've kind of always wanted to host, but just never really had the need or anything to really push me over that edge to host, was like a Git repo for myself that I could just host, on my home network, and it would be great. But if this actually holds true, and GitLab is planning to delete dormant accounts after a year of quote-unquote dormant-ness, then I think I found my reason to be able to make my own Git repo. But the one thing that I really want to hammer home here is, just because code hasn't been updated in 12 months doesn't mean that it should be scrapped and it's like dormant and never used. Because, like I mentioned, some of the code that I have in my repos, I don't update anymore, since there's nothing to update on them, and they're basically just there as a reference. I don't need to make any updates to it. But even still, like, if you have something in production, just because hasn't been updated in a year, that doesn't mean that no one's using it. Like, for instance, you could have a piece of code that's, being used heavily, but it just hasn't had any bugs, vulnerabilities, or anything like that come up, and there's been no need to add any new features, so there's been no point to update the Git repo. So the idea that just because a repo hasn't been updated into 12 months means it's been, like, abandoned or dormant or whatever is just not true in most cases. Plus, you also have to figure, if you've never worked with coding or programming or anything like that before, Git repos are pretty darn small. Like, unless you're writing some massive project, or you accidentally like include all the libraries and dependencies that you're using for a big project in the Git repo. Like if you're just talking about, the average Joe's Git repo of his, fun project he worked on, we're talking about kilobytes here. Maybe megabytes if it's like a fairly, bigger project, but we're talking about like kilobytes, basically insignificant amounts of data with the scale that, a company like GitLab is hosting, where they're talking about, terabytes or petabytes worth of data, which kilobytes is nothing when you're talking on that big of a scale. Now, obviously, there are the outlier cases where you have, massive code repos because someone pushed the entire library and all the dependencies up and whatnot. But that's definitely an outlier. The majority of cases, it's, these really small repos that in reality probably don't, take up a ton of space. Now, it is if this is true, I will say though, if this does turn out to be true and they do implement this, I can guarantee you that they will not have to worry about storage being an issue anymore. And the reason for that is because everyone's going to leave, right? Because if you know that if you push your code to this platform and if you don't touch it for a year, it's going to be gone, do you want to take the risk of potentially losing your code because you didn't touch it for a year and some company thought, oh, it can go bye-bye now because they haven't touched it in a year? I mean, I wouldn't. Because just because I haven't touched, a piece of code in over a year doesn't mean that, like, I might not want to come back to it later, or I might want to reference it later or something, and I might want to use it. So just because it's quote-unquote dormant doesn't mean that, it should be gone. So I will say, if this is true and this does start happening, I think developers are going to start leaving by the boatloads. And in that case, all their dormant code is going to be gone and they're just going to have a lot less users and their storage problems will be solved. Because if you have a ton of less users, then, your storage issues magically disappear since there's less people using it. But realistically, hypothetically, if this is true, they're having issues with storage space and the cost of it, they could just archive the data rather than just getting rid of it forever. Like, there are very cheap cloud archiving solutions out there, and which are a lot cheaper than, fast access stuff like, on Amazon, I think it's their EC2 or whatever is like their kind of big thing for running, servers, and then they have like different storage tiers and all this stuff, but they also have like archival stuff too, which is, cheaper. So if they're really having trouble as far as finances go, they could just push this quote unquote dormant code to like an archival process. So it's still available if you want it, but like you just have to like reactivate it or something, and then you can, get it back or something, not delete it. But, we'll see what happens if this actually turns out to be true. But I thought it was interesting and worth pointing out, since this is definitely some big news in the developer world. And who knows, maybe on next week's episode, when I talk about the nerdy things that I did this week, you might hear about me installing a Git repo in my home network and starting to use it and my thoughts on it, which I do think it would be cool. I have used in my professional work, installed Git repos and used Git repos like internally rather than like a one on like GitHub or Bitbucket or anything like that. Like I've deployed and used internal Git repos, so it's not something foreign to me. And I do kind of like it, but we'll see how it goes with my personal projects. So the next thing, it occurred to me of how antivirus really works. So I've mentioned before on this podcast about antivirus and how I'm generally not a fan of it. I talked about kind of Windows Defender and it kind of spying on you, essentially, which really all antivirus spies on you, because if you think about it, the only way that it can detect viruses and new viruses is if it's constantly scanning your files and looking for signatures and all that stuff, and looking for anomalies, and then reporting that back to Norton or McAfee or Microsoft or whoever the owner of the antivirus is, so they can, add that to their database and deploy it to every other machine using the antivirus, so you can have a more useful and protective antivirus, right? But I think the real way that antivirus works is it slows your computer down so much, kills the battery so quickly, which I guess if you're on a desktop, that doesn't matter. But it slows it down so much, hogs so much of your resources, makes your system so unusable that you just don't use it, and then you never get a virus. I mean, it's genius, right? If you never use your computer, you will never get a virus. So if the antivirus program can just force you to never use your computer because it makes your experience using that computer so bad and so slow, you just won't use it. Which, ironically, is basically what happens if you install a virus on your computer. It becomes so slow, so unusable that you just can't use it. Of course, if you have a virus, you can just reinstall your operating system and then you're good to go. Just like if you want to get rid of your antivirus easily, you can just reinstall the operating system and you're good to go. But yeah, so the reason why this thing occurred to me, that maybe this is the true reason of what antivirus is doing, is because one time I was using my computer and it was just running so slow. It was running slower than molasses in January, and I decided, you know what? I'm going to see why this thing is being so slow. So I open up the task manager and I see McAfee Antivirus was using basically all of my system's RAM, which, granted, it was only 8 gigabytes of RAM, which isn't a lot, especially on Windows, but still, it was using like all the RAM. And at one point I saw it was using basically all the CPU also to quote unquote run scans. It was running scans. Okay. Anyway, it bogged down the system so much that I literally couldn't do anything. And the reason why this happens, as you can expect, is if all of your system RAM is gone, what your operating system then does is it goes to your disk and uses what's called a swap. And the point of the swap is basically to act as like an extension of your RAM and kind of use your hard drive or SSD or whatever you have for your long-term bulk storage as system RAM. Now, if you have an SSD or a solid-state drive, this is obviously slower than RAM, but it's not like super terrible. Like it's obviously slower, but it's not like unusable. Now, if you have a 54 RPM hard drive, like my computer had, that just becomes unusable. Because if you've ever used a computer with a 54 RPM hard drive, you know that it takes forever to open an app for the first time. I mean, once you open the app for the first time and it's been open, then it's not that bad because it's in RAM and RAM is fast. But the first time having to load that from the disk and put it into memory and get all your stuff set up and all that jazz, it takes a while. Now imagine that process every time you want to not only open an app, but do anything in the app because it's running off the disk rather than off of RAM. Now you can see why this makes your computer basically unusable. Because we all know that a 5400 RPM hard drive, which is already slower than a herd of turtles running through peanut butter, is trying to load applications for the first time is slow. Now running everything off of that rather than RAM, you're in for a bad time. So, which the reason why running things off of RAM is just so much faster is because it's closer, as far as the architecture of the computer is concerned, the RAM is a lot closer to the CPU. Plus, it's able to access it a lot quicker rather than having to go all the way. Because when a CPU is trying to get the data that it wants, it first goes to its cache. So the CPU itself, the brains of the computer, has memory on board, and that memory is super fast. And then if the data it's looking for isn't on the CPU itself, then it'll go to your system's RAM. And if it's not on the system's RAM, then it has to go out to your disk, fetch it from the disk, and then bring it into RAM, and then load it to the CPU's memory. So there's a lot more steps involved. And obviously, if you have a hard drive, it takes a lot longer to read the data in the first place, which makes the whole process even slower. So that's why that's kind of a crash course in operating systems and computer architecture 101 right there for you. So yeah, if you're trying to use a 54 RPM hard drive, or really honestly any kind of drive in general, like even solid state drives as RAM, you're not really in for a good time. So good luck being productive, that's for sure. Which, talking about slowness and trying to speed things up, that's a great segue into multithreading and multiprocessing, because the whole point of multithreading and multiprocessing is to make your code and your programs faster. So they sound similar, which they are, and sometimes I think people kind of use them interchangeably, which is not good, in the sense that while they are similar and they both provide speed up in your program and can make your program run faster, they work in different ways. Which we're kind of going to go over, and we're also going to go over some of the issues and challenges which you can run into, and why generally, at least in my case, and I think in a lot of cases, multi-threading and multiprocessing is kind of an afterthought and kind of implemented later rather than going in to a program, unless you know you're going to need it. Generally, you start kind of with just one thread, one single process running, which we'll get into what that means here in a little bit. So you're just running with one thread, one process, and then eventually you might get to the point where you realize, this is kind of slow. I want to speed this up, and that's usually when multi-threading and multiprocessing comes around. So both of them are just ways of achieving parallelism, which basically means that you're running or performing multiple tasks in parallel or at the same time. But the reason why it's generally not the first go-to thing when writing a program is it can be kind of tedious and difficult to implement, since there's a lot of things that you have to think about because you have two things running at the same time. If you have things that are dependent on one finishing before the other, that's another thing you have to take into account when you're writing your program. So if my program needs to wait for variable A to have a value, and before I can compute the final result of B, you have to, if you call value of A before value of A has been computed, you're not going to get the right answer. So you kind of have to, think and put some thought into making sure that everything is done, with its process, because it doesn't run sequentially. So trying to do multi-threading and multiprocessing is kind of almost takes a different way of thinking, because normally when you're writing a program, everything goes sequentially, right? Like I do step A, then I do step B, then I go to step C, then I run through this loop, and then I get to step D. But if you're doing multithreading or multiprocessing, you might run into a situation where you do step A, and then you do step C, and then step B, and then step D. And if your code relies on that sequentialness, you're in for a bad time unless you can, unless you actively program in, ways to make sure that things happen in the order that they're supposed to when they matter. Which we'll get into some examples of that. But another thing you kind of have to worry about is overwriting shared memory or any kind of shared resources like a file. Specifically, the shared memory and shared resources type thing is more related to multithreading rather than multiprocessing, because multithreading, everything's running in the same process in the same memory space, whereas multiprocessing runs in a completely separate process with its own memory. So generally, if you're doing multiprocessing, overwriting variables generally isn't an issue. Whereas multi-threading, you really got to watch out for that. But both of them will have the issue of, if you're trying to write data to a file, you'll have to make sure that another process or another thread isn't also writing data to that file, because then you're going to overwrite stuff, and again, you're in for a bad time. So a lot of, basically kind of the moral of the story here is multi-threading and multiprocessing aren't like, they don't necessarily make logical sense in the sense that you have to put an additional thought into making sure your code will work. And the other thing that's really annoying about multi-threading and multiprocessing is errors. And the reason why is because it's insanely hard to debug any kind of program that uses multi-threading or multiprocessing, because you're not always going to get the same result every single time. Sometimes it'll work perfectly, and other times it'll error out and you'll get a bug, and you don't know why. And it's insanely hard to replicate, because, like I mentioned, sometimes you'll have step A, B, C, D. Other times you'll have step B, D, A, C. I mean, it can kind of run in whatever order. And that's kind of partly has to deal with how the operating system schedules tasks and whatnot. But yeah, it can be a real pain trying to debug that, which is, I think, part of the reason, at least in my case, that when I have to write something with multi-threading or multiprocessing in mind, that I make sure that I have a sequential program that works. If I can write it sequentially and it works, I know at least my baseline is good. And then I can start implementing in the multiprocessing or the multi-threading or whatever, and then hopefully I won't have to run into as many issues. Obviously, I still always run into issues, because whenever you write code, it doesn't matter how long you've been doing it, you always run into some issues because bugs get in all the time, as we mentioned in a previous episode of the Dark Assassins podcast, talking about bugs. So kind of get into some of these problems that can come up with multiprocessing and multithreading is this idea of a race condition. So the idea of the race condition is you're trying to read data at the same time, and then you're also like trying to write at the same time. So an example of this is, say you go to deposit money into your bank account, but also at the same time, your credit card payment is also being deducted from your account. So a race condition can occur here when you both access the account at the same time. So you read that your balance is $200, and the credit card withdrawal reads that your balance is $200, and then you go to deposit $50 that you got from, I don't know, it was your birthday or something, and your grandma gave you money, so you deposit that $50 into your bank account, but right after that, the credit card is also withdrawing $100 from your bank account. So in theory, if you had $200 and you put in $50 and then the credit card withdrew $100, you should have $150, right? But because of the race condition, what can happen is you'll actually be left with $100 rather than $150. And the reason is, if you both read the $200 at the same time, and you both write, then what can happen is the credit card could overwrite your write. So rather than you writing $250, because when the credit card read that it was $200, it thinks there's only $200 in there and hasn't read the update that you put in that you now have $250, and then it deducts $100 from $200 and writes that. So now you have $100, and you should have $150. So that's obviously a problem, and that is a race condition. And the way that you can prevent that is by using what's called a lock. And the point of the lock is to basically say, okay, I'm going to access my account. Let me lock down this variable here so no one else can read it or write it or touch it, to make sure that this race condition of the numbers being overwritten doesn't happen. So in this case, if we go back to that example, you're trying to access your checking account, and the credit card withdrawal is also trying to check the checking account. So first what happens is you get to it first, so you put a lock on it, so the credit card is just waiting there. And then you can deposit your $50, release the lock, and now you're correctly at $250. And then the credit card company sees that the lock is open, it's available, so they grab the lock. They see that you're at $250, they subtract the $100, and now you're at $150, which is where you were supposed to be in the first place. So problem solved. So that's how you fix the race condition. The problem with the race condition and using locks is you can run into another problem, which is called deadlock. So the reason why this happens is if you add locks into the equation, you could run into a scenario where you lock something and someone else locks something, and you need the thing that they locked and they need the thing that you locked, so you're both just stuck there waiting for the other person to release the lock, and you can't do anything, and you run into deadlock. So an example of this is, say that you and I are trying to send each other money. So I need to lock your account to prevent a race condition, as we mentioned just before, because obviously that wouldn't be good. And I also need to lock down my account, again, to prevent the race condition. And you need to do the same. You need to lock my account, and you also need to lock your account. So if we're both trying to send at the same time, we both lock our accounts, and then we're going to try to lock the other person's account. But obviously, the accounts are already locked, so we're stuck in deadlock, because I'm waiting for you to release the lock on your account, but you're waiting for me to release the lock on my account. So we can't do anything. So that's, some problems that you run into when dealing with multithreading and multiprocessing that you really have to think about when coding up your programs, which obviously, if you're just doing everything sequentially, this is never an issue. So there's definitely an art and a lot more thought process that goes into it. So let's go kind of break down some of the differences of when you would want to use one over the other. So multithreading is more for and better for I/O-based tasks. So think of this as you're handling file inputs or handling keyboard inputs or any kind of like input-output type stuff. Because if you're waiting on something, say I'm waiting on you to give me input, I can be doing other stuff in the background, like other processing or, whatever the program needs to do. And also the other thing with multithreading is this, I think I mentioned this before, but I'll mention it again. Multithreading just uses one single process with shared resources and create multiple threads for each operation. So basically, what a thread is think of a thread as just a singular piece of an overall process, right? So say I have a multi-threaded application, and I have two threads. One thread handles the user input, and one handles what to do with that user input once I got it. So say you give me numbers and I compute the sum of them, right? Rather than having to always, the sequential version would just be one single thread, which would take the input and then process that input. Whereas the multi-threaded process would have 2 threads, one that receives the input and can always be just receiving input nonstop, and the other one can be processing that. So the reason why this is good is if you, say, have a big chunk of, calculations that you have to make, or you have to write a ton of data to a file, rather than you reading in, that input, and then the program, what appears to look like it's just hanging and no longer responding because it's doing things in the background, you don't have that problem because you're able to continue to take input in, and you can have another thread off doing the computation or whatever the case may be. So that's kind of, some of the benefits that you can have for multi-threading. An example that you could think is if you're trying to handle, like I said, user input, and then one to process that, so you're not always having to wait for the prompt. But one thing, it is less overhead than multiprocessing, because you're just spinning up multiple threads in a singular process, so there's not as much overhead. But there is more overhead than if you just wrote it all sequentially. So if you just wrote a single program sequentially, you're not having any overhead, in the sense that you don't have to, go to the operating system and, request, more threads to run things at the same time. But how this differs compared to multiprocessing is more for like computational bound tasks. So if you need, lots of, raw processing power, this is where you'd want to do multiprocessing. So an example of this is I actually wrote a program. I guess I can get into another example for multi-threading, but we'll stick on multiprocessing for the moment. I wrote a program to basically simulate what mining Bitcoin is like, which it works. It's not good as far as a Bitcoin miner, and obviously it's not a Bitcoin miner because it doesn't connect to the Bitcoin network. So if it's cold in your house and you want to turn your computer into a space heater, it's a perfect program for that, because it'll max out your CPU and just make that thing run, draw as much power as it can, and just heat up. So if you need a space heater, it's the program for you. But the point the reason I bring this up is it obviously having to compute hashes and whatnot is pretty computationally expensive. So being able to add as many cores as possible and to be able to just run a ton of computations, that is like the crux and the definition of a use for multiprocessing. So like I mentioned before, multiprocessing uses multiple CPUs rather than just multiple CPUs for each process rather than just having a singular process. Unlike threads, each one of these processes has its own memory space and own resources. Unlike threads, which is because it's all in the same process, it shares, all that memory and that all those resources. So another kind of example that you can think of for multiprocessing is, say you want to the most basic example that people talk about when it comes to multiprocessing is, say you have a really large number that you want to count to. And what you can do is, rather than having a singular process count from, say, 0 to, 20 billion, rather than doing that, what you could do is, if you, say, had 4 CPU cores, you could divide that 20 billion into 4, give each one of the processes basically a fourth of that 20 billion, and have them count, and you'll finish the task a lot quicker. Now, obviously, because you're having to actually get spin up different processes on different CPU cores, this is obviously there's a lot more overhead initially than compared to something like even multi-threading, or obviously just running everything sequentially. But if you're doing like a really big computational task, like, counting to a really big number, or a Bitcoin simulator or whatever, the speed benefit that you're going to get definitely outweighs the overhead. But if you're just doing something really small that doesn't take a lot of processing power, and you're basically just doing multiprocessing for the sake of multiprocessing, then you theoretically could see it being slower with multiprocessing because of all the overhead of having to, make those processes and then join it back together. And the same thing goes for multithreading too. You can run into scenarios where because of the overhead that's involved in creating those threads and joining them back together, it could actually be slower to do it multi-threaded rather than just single-threaded. So that's one thing that you do have to test and analyze per use case, if it's actually something that's right for you. If it's a really big project and there's a lot of things going on, then it's more often than not probably better, and you actually will see speed ups and speed performances doing multi-threading or multiprocessing. But if it's just a simple basic application, you might actually be slower to do multi-threading or multiprocessing, which is another reason why a lot of people, when they're just writing, simple scripts or personal projects or that kind of thing, they don't even bother with multi-threading or multiprocessing, because in addition to all those things you have to take into account, like we mentioned before, like the race conditions and the deadlock and all that stuff, it could even just be slower doing that rather than just running it just as a single thread, a single process. So there is that aspect to it, plus it's just easier, right? If you're to just write something sequentially. So those are the general reasons why people don't use it a whole lot. But going back to the multi-threading application, I mentioned I had a program that I wrote a C program, which is basically a server that'll take in requests. And the reason why multi-threading is good here is because if you have a lot of people coming in for requests, you don't want your system to have to be able to accept a request and then take the time to do whatever it needs to do and then return that result. Because if you have 10 people trying to access your server at the same time, you want to be able to service all those people at the same time, right? And if you're only running a single threaded application, you're not going to be able to do that. So the reason why you'd want to have threads is so you could, have multiple threads listening for connections and then be able to handle them all, individually at the same time. So you can handle a lot more people, and it can, greatly speed up your server. So that was that application. A more practical use case. But even that, if you're doing a server, for example, in this case, that is prime target for a denial of service attack, because all someone has to do is flood you with a ton of requests and just sit on them and not do anything, and then your server's down. Can't do anything. But there are, other things that you can do to prevent that. You could potentially, if that you're supposed to get from a real request, say you're supposed to get something from them, in, I don't know, say 3 seconds. If you don't get something, you can just terminate the connection and move on to the next one. Or if you have a load balancer and multiple servers running the same program, you can distribute the load across multiple servers, so it makes it harder for an actual denial of service attack to be successful. So there are some ways you can mitigate that. Obviously, if you have a firewall or an intrusion detection system, you could have that running to detect for something like this and stop it before it even happens. So there are ways around it, but just at its core, this program was susceptible to a denial of service attack. But the point of the server, right? It was just for an example for myself to be able to have an example of how multi-threading works in C or C++, which, going back to the GitLab potential debacle, I should say, since as far as I know, GitLab hasn't actually confirmed this or even denied it, so it's just kind of, I guess, as you could say, in the rumor mill or whatever, which I guess, in fairness, that server program is on my GitHub, not my GitLab account, so it really wouldn't matter anyway. But regardless, that server program is probably one of those things that I'm probably not going to touch again, just for the point of, if I want to actually make a server, I'll either clone it or copy the code that does the multi-threading and then, do some other implementation of it, right? Or use that code as a reference rather than, making other modifications to it, right? So we brought this episode full circle, didn't we? Started talking about GitLab, and then we get all the way through talking about antivirus and multithreading and multiprocessing, and tie it all the way right back into GitLab. Now that is how you write a good podcast. Just kidding. That was just total happenstance of how that came up. I'm not that slick, not that clever. You might think I am, and if you do, I thank you for that. But no, that this was just total happenstance. But since, I figure since we did such a great job tying this all back together, I guess that'll pretty much do it for this one, since I ended on such a good note. So if you enjoyed this episode, I ask that you leave a rating and review, and subscribe to the Dark Assassins podcast if you haven't done so already. Also, be sure to share with a friend or family member who you might think would be, especially if you have any friends that are developers and have GitLab accounts, they might definitely want to hear about this. Also, if you have a friend or family member that's interested in learning about multithreading or multiprocessing or just anything we discussed today, please share it with them. And if you have any questions about this episode, or you just have any questions in general that you want to ask me, you can shoot me an email at contact@darkassassinsinc.com, or you can click the link in the show notes below. And that's going to do it for me in this episode of the Dark Assassins podcast. Until next time, my fellow assassins, remember, bool nothing equals true. If action not equal to null, return true. I'll see you next time on the Dark Assassins podcast.